Welcome back to Analog Electronic Circuits, and today is lecture number 21. We are going to discuss the cascode differential amplifier as well as two-stage amplifiers. This is stuff that we have learnt in the single-ended world, but now we are going to make differential cascode amplifiers as opposed to single-ended. So, let me actually modify the title. Differential cascode amplifier and two-stage amplifiers, because we have already done the single-ended cascode amplifiers once. And then yesterday in the last class we were working on this differential cascode amplifier. We said that the small signal circuit is just like the small signal differential mode half circuit is just like the regular cascode amplifier. In fact, it has to be the same, right. That is the entire point. Okay, it has to look like this. This point is ground, but I am not marking it ground right now because I am just going to change it, right. This is ground in the small signal half circuit. Okay. This is the regular cascode amplifier. You apply your signal here, you get Gm times the signal as the current. This signal tries to, so we are looking at short circuit current, right. So, in the short circuit current experiment, you have shorted the output. You applied a voltage here that created Gm times the current. This Gm times the current is trying to split between RDS and what you see looking into the source. Now, what do you see looking into the source? You see 1 over Gm of this device. 1 over Gm of this device is a low impedance. RDS of the bottom device is a high impedance, which means that effectively almost all of the current that was created by this voltage, that is Gm times the input voltage, is going to go into the source and therefore into the short circuit. So, the short circuit current is almost equal to Gm times V in, and if you want to figure out exactly what it is, then you have to work out the current division ratio, that is the current division between RDS and 1 by Gm in parallel with RDS, right, of the second transistor. So, this current division you work out, and that is the ratio by which Gm is going to be reduced slightly. So, effectively the short circuit transconductance is nothing but Gm. Second experiment is output impedance. When you look in from the output, you see you can look upwards, you can look downwards. So, it is the up resistance in parallel with the down resistance. The up portion of the resistance is intrinsic gain of this MOSFET times RDS of the second one plus RDS of the first one. Okay. That is the up resistance, and the down resistance is nothing but intrinsic gain of this MOSFET times RDS of the second one plus RDS of the second one plus RDS of the first one. Okay. So, this is generally going to be a large impedance. You can approximate it as the intrinsic gain of this device times RDS in parallel with intrinsic gain of this device times RDS. Okay. So, you can approximate it, and therefore, your gain, your voltage gain is effectively. So, now let us. So, if you want to work out the approximate voltage gain, it is nothing but Gm1 is the transconductance approximately, and the output impedance is Gm2 RDS2 times RDS1 approximately in parallel with Gm3 RDS3 times RDS4. Okay, so this will be a minus sign because the short circuit current is coming backwards. So, this is effectively the small signal voltage gain. Okay. Now, this is the small signal voltage gain of the differential mode half circuit. So, therefore, what is the complete circuit? The complete circuit probably can look like this. All right. This is how the complete circuit is going to look like. Any questions over here? Okay, so one question is that why am I not connecting these two together? They can be connected. You can do whatever you want. This is just one of the many possibilities. You can place a current source in between these two also. It makes no difference. Okay, actually you can't pull currents through gates, but anyway, you can do whatever other things, fancy things you like, no problem. Any other question? You can be creative. Any other question? Okay. So, be creative. You can put a current source on the top also if you want, no problems. All right. Now, this is still the small signal picture. You are going to apply V in positive over here, V in negative over here in the small signal. This is still the small signal picture, and now you have to incorporate the operating point conditions. How will you incorporate the operating point? I mean, are you going to connect this to ground actually? No, right? You are going to connect it to just the right voltage such that half of this current flows through it. Okay. So, in other words, what you are going to do is you are going to connect these gates together. You are going to assume I naught by 2 is coming this way, I naught by 2 is coming this way if this is I naught. And that means that this gate voltage has to be just right such that the PMOS current is I naught by 2. Right, which means that you probably are going to use something like this. Fine. Now, this is okay. I have not yet connected this portion up. This is a straight line. This is I mean, imagine this to be connected. Now, the biasing of this device is done. What about M3? Are you going to ground? It is okay to ground, but ground is not optimal. Right, ground is not the optimal voltage. For example, you could have done a Wilson current mirror, you could have done a modified Wilson current mirror, you could have done something more optimal than the Wilson current mirror, okay, less accurate but more optimal. You can do all kinds of those things. So, let us just imagine Wilson for now, in which case this is what is there. Okay, now I have drawn the full line. Okay, so, both of these voltages, they are not really ground, they are some voltage which is created by a current source. Okay, these two current sources have to be matched now, right. If this is I naught, this needs to be I naught by 2. How will you do that? This is also going to come from some reference current source. Let us say I naught by 2, and then you are going to mirror it with a MOSFET, and this is going to be of size, I am sorry, what did I do? Okay. Okay. So, you have got a mirror over here, this is going to be of size 2, 2x of this size. So, that if this is I naught by 2, then this is double. So, I naught, and this is the same. Okay. Done. What about these two nodes? What should that be? That can be anything. Actually, it can be anything as long as it is larger than a certain value, right, but then you can be optimal, right, so that you get the maximum possible swing over here at the output. So, you can try to optimize. Once again, you have to work out what is the input common mode voltage. So, given an input common mode voltage, then only you have to set that, for example. Okay. So, for now, for example, this could be VDD, this is going to work, no problem, VDD is perfectly acceptable. Why is VDD acceptable? Okay, let's draw it up. Let's draw up this entire thing on the next page on a clean slate, and let's take some numbers and analyze the circuit. So, I am going to draw up the whole thing. Okay. So, this is my setup, all right. This is my amplifier. Where are the outputs? It is 2 inputs, 2 outputs, fine. Now, let us put some numbers. Let us say my power supply is 2 volts, okay, and let us say that I like VGST of 0.2 volts, and let us say VT is 0.5 volts. These are just numbers that I am throwing at you, just because I like these numbers. Okay. So, for my given current source, I would like this node to be at 0.7, all right. So, I am going to size this device such that this node is 0.7, 0.5 plus 0.2 of VGST. This device will require 0.2 volts of VGST which means that to place this nicely in saturation, the minimum voltage here is 0.2. Okay. This is also at 0.7, and likewise the minimum voltage here is 0.2. Okay. So, these voltages have to be greater than 0.2 to make sure that the devices are in saturation. All right. And let us say that the PMOS also happens to have a VT of 0.5 volts. Okay. You want a different number? Okay, fine. Let us say the PMOS has a VT of 0.4 volts. Okay, just just throwing numbers. So, 0.4 volts of VT, and I would like the PMOS to also have a VGST, that is VGS minus VSG minus VT of 0.2 volts, which means that I want VSG to be source to gate voltage to be about 0.6 volts, which means that when I pull this I naught by 2 of current, just by the way, this is 1 unit, this is 2 units, this is 1 unit. These are all 1 units each. And normally what is done is you scale this down and you scale this down so that you do not waste current. Okay. So, you might want to make this 0.1 unit instead of 0.1. Okay. And then again you might want to make this also 0.1 unit. When I say 0.1 unit, what is 0.1? This is the ratio of the W by L's. So, W by L is not 0.1. Okay. If this has a W by L of 100, then this will have a W by L of 5, 20 times smaller. That is what I mean. Okay. That is all. So, for example, if this has a W by L of 50, then this should have a W by L of 5. Okay. And if this current is I naught by 20, then this current will be I naught by I naught, this current will be I naught by 10, I naught by 20, right. This current will be I naught by 2, and so on. So, this is something that would actually be done. You will not really keep things that equal. Okay. So, this is my overall scheme of things. Minimum voltage here is 0.2, okay, but the PMOS, this particular PMOS will require 0.6 volts of VSG, right, because we picked VT is 0.4, which means that the voltage here at the gate of the top PMOS is required to be 1.4. Okay. So, the drain of the top PMOS is also 1.4, which means the gate of the second PMOS is 0.8, and this is satisfying this requirement. Okay. So, all these are happy over here right now. Great. Next, let us look up over here. This is at 1.4. What is the maximum voltage at this node? Maximum. Then we will just figure out what it is exactly. What is the maximum allowed? The maximum allowed is 1.8, because I have 0.2 volts of VSG minus VT. Sorry, it should be less than 1.8, but what is it actually? This node is 0.8, this requires a VGST of 0.2, that means this is 0.6 volts above. So, this is actually 1.4. Okay. So, this node is actually at 1.4 and it is satisfying the fact that it is less than 1.8. So, it is not really optimal. Okay. For an optimal situation, it would have been exactly at 1.8. It is not optimal over here, and the reason why it is not optimal is because of this Wilson current mirror. You can make a better current mirror. So, this node is exactly at 1.4, this is also at 1.4, this is at 0.8. All right. Next, let us figure out what is the maximum voltage over here. This is at 1.4, VSG required is 0.6, VSG minus VT is 0.2, which means that V source to drain has to be at least 0.2 volts, which means the maximum voltage at this node is 1.2. Okay, it can't go higher, because if it does go higher, then this device falls out of saturation. It does not really damage things that much, because there is graceful degradation. This is a nice Wilson current mirror. However, you can say that this is the maximum that you are going to tolerate for best performance. All right. What is the voltage over here? 2. Okay, 2 volts. I have hooked it up straight up. So, 2 volts is the voltage over here. What is the minimum at the output? 2 minus VT, right. If this is 2, then this is 1.3, 0.7 volts of VGS. So, this is 1.3, means that this can be this has to be at least 1.5. So, we have a violation, right. This NMOS is saying that the voltage here has to be more than 1.5. The PMOS is saying that no, the voltage here has to be less than 1.2. So, in either case you have a conflict, and therefore, this can't be at 2 volts. This has to be placed lower. So, that is why I said, is it really okay to have 2 volts over there? No, it is not okay. You need a lower voltage. Okay. All right. So, we will place a voltage over there. Let us go from bottom up. Okay. So, what is the lowest voltage over here at the input? Input common mode has to be more than 0.7. Okay, as long as it is something more than 0.7, then this node is going to keep the bottom tail current source happy. All right. So, let us assume some number. Let us say that the input common mode voltage I have set it to 1 volt. Suppose 2 volt is the power supply. Let us keep the input common mode at 1 volt, half of the power supply, and this is coming from outside. All right. So, the bottom device is happy. Why? Because VGS is how much? 0.7 volts. So, this node is actually at 0.3, which keeps the bottom device happy, because it is more than 0.2. Great. Now, what is the lowest voltage at this node? Lowest allowed voltage. This is at 1. So, this must be at least 0.5, if not more. Okay. Now, supposing it is exactly at 0.5, then this device is just about happy, right. There is no flexibility, just about happy. In that case, what will you apply at the voltage over here as the voltage over here? 1.2, right. If this is exactly at 0.5, this has to be exactly at 1.2. So, the voltage here has to be certainly more than 1.2 in that case. Okay, we tried with 2 volts, which was more than 1.2, but with 2 volts I did not have an output. So, if I apply exactly 1.2, then what is the lowest voltage at the output? The lowest voltage at the output is 0.7. Okay. So, let us not apply, let us not be so tight, let us make it 1.5, let us say, or you want 1.7. Okay. So, let us make it 1.7. If I apply 1.7 volts over here, then what is going to happen? The voltage here will be 1 volt, which is okay, perfectly fine. 1.7 here, 1 volt here. What is the least voltage over here? 1.2. Okay. So, the voltage here can't be lower than 1.2, which means if you have 1.2, you are just about right, there is no possible swing, which means the voltage out here has to be actually less than 1.7. So, 1.7 if I keep the voltage here at 1.7, then that is really so high that no swing is allowed at the output. Okay. So, you have to place this judicially, place these voltages intelligently, you can't just place random voltages. Okay. In that case, how do I generate this voltage? How are you going to generate this voltage? Is, for example, how will I get a number between 1.7 and 1.2? Well, place one more. So, I have got 0.7, then I will get 1.4 over here. 1.4 is very reasonable. Okay. So, you have to do these things a little smartly, it is all on a case by case basis, and you have to be a little creative about it, right. You have to see what is the VT of the device. So, you have to work out all the swings, you have to work out all the VTs, work out all the swings, the VGS minus VT, see exactly what is required, and accordingly creatively make your circuit, design your circuit. And these are the general guidelines. The general guidelines are that you need some swing, right. A cascode, you can use cascoding to generate other voltages. I naught by 20 current is going through. So, this has to be of size 0.1, right, because then only it is going to generate 0.7 volts of VGS minus VT. Okay. Sorry, 0.7 volts of VGS, that is what you need. Okay. And then you apply this, this is of course of size 1. All right. This is your telescopic cascode amplifier. Now that I have placed 1.4 volts over here, which is both less than 1.7, more than 1.2, is this node, what is the voltage here in that case? 1.4 minus 0.7. So, this is exactly at 0.7, which is fine, and the lowest voltage over here now is 0.9. So, the output voltage can now swing between 0.9 volts and 1.2 volts, just 300 millivolts of room at the output, not very much. Okay. It is not a lot of room, and that too my input is exactly at 1 volt, right. It is not at the lowest limit, it is not, it is just 100 millivolt above the lowest limit. The lowest limit was, what was the lowest limit? Sorry, this is not 0.7, this should be 0.9. Okay, the lowest limit is 0.9. So, it is a little bit above the lowest limit. This device is barely in saturation. Okay. So, 100 millivolts you can increase over here, maybe, right. On the bottom side you might be able to increase by 100 millivolts, but there is not much room. All right. So, what is the is there this is a good design or not? This is generally a good design, just that there are too many devices in a stack, okay, and each of these devices are eating up headroom, right. They are all eating up headroom, which is leaving not much room for the output nodes to swing. Okay. So, if you want the output nodes to swing more, what do you have to do? You have to somehow re-engineer the circuit such that the stack size is not 5 devices, it is less. Okay. The stack size cannot be 5 devices. Okay. If you reduce the stack size, let us say if I manage to make it 4 devices, immediately I will get a performance benefit over here. The swings are going to, right now the swing is just 300 millivolts at each output, right. If I can reduce by 1 transistor in the stack, then immediately that 300 millivolts might become 500 or 600 millivolts. Okay. So, we are going to see that. All right. So, this is called the telescopic cascode amplifier. Why is it called a telescopic cascode? Because it is like you have stage after stage, you know, the telescope opens out. So, that is, it is just a name. So, this is called the telescopic cascode, in this case differential amplifier, fully differential amplifier. Next, what we are going to study is called a folded cascode differential amplifier. What we are going to do is we are going to try to reduce one out of these 5. Okay. Can we fold it? Let us say, can we make this one of these as a PMOS, right, and then fold the structure in a way that it still works. Okay. So, let us go back to my half circuit. My half circuit looked like this. All right. Now, what if I say let us twist this and can I make this as the half circuit also? Is this also a good half circuit? Of course, this is also a good half circuit because it is exactly the same, okay, just that I have twisted this bottom device up, right, and in the small signal picture, incremental picture, there is no difference between NMOS and PMOS. So, this is also an equally good half circuit, and if you place a current source over here, you can go ahead and place a current source, then this will also work. A current source would be an NMOS in this case. Okay. This is also a good circuit, reasonably good circuit. All right. So, now what we are going to do is we are going to redesign our circuit with this as the basis. This is going to be the half circuit. All right. So, the plan is that I will have this as my half circuit and then regenerate the complete circuit. Okay. Where is the tail current source going to be? So, the tail current source used to be over here, now it is going to be here. And then you mirror. All right. So, this structure is called the folded cascode. Let us look at it, let us draw it nicely. So, these are my two inputs. I am sorry. Okay. So, the first thing you should notice is that my stack size has reduced. I have now got a stack only of 4 transistors. Okay. This is not the complete thing, this is still the small signal incremental picture. I have converted the differential half circuit into a full circuit. All right. Next we have to do the bias, the DC operating point. This is fine, right? You can. Okay. So, for the DC operating point, what is the plan? If this is I naught, if the tail current is I naught, then you expect these two currents to be I naught by 2 each. Okay. So, I naught by 2 current is flowing this way, and remember in the earlier case, in this particular case, you wanted the same current to flow through the load, the active load, right, which means that you would want. So, this is your active load, right. These two currents also to be I naught by 2. Which means that these two MOSFETs, these are current sources. Remember, this was this one. We said let us add a current source here. Okay, so this MOSFET is actually a current source. So, these two MOSFETs should be drawing I naught each. Okay, of course, you can rework this. This does not have to be the case. This could be 2 times I naught, then in that case this would be 5 I naught by 2, and so on and so forth. You can rework the numbers according to your design, but this is the overall strategy. All right. In that case, what do you have to do? You have to make all of these currents out of current mirrors once again. All right. So, you are going to have this gigantic current mirror. It is going to mirror out I naught over here, and then similarly you are going to create the voltage here, the voltage here, the voltage here. You want me to redraw it, redraw the whole thing, want me to draw it just like we did last time and discuss the swings? Yes, okay. So, let us draw the whole thing. Okay. The plan is that these two will not be ground, these two will come from a current source, right, and likewise these two will also come from a current source. Okay. And then maybe a mirror of that is going to generate I naught by 2 . Okay. So, another mirror, a cascode mirror, copy of copy, and then you are going to generate these voltages. Okay, let us draw it. There is no space on this page anymore. So, let us draw it nicely. Okay, so this is my output stage. Where is the current coming in? The current is coming in over here from the input stage. Okay, and let us make my input stage. These are my two inputs joined together to make a current source. Current source will also be a p channel MOSFET, that is the tail current source. All right. So, this is my structure, and now I have to work out all these individual gate voltages. Okay. So, let us take out a reference current. We always start with a reference current, and where is this what is inside this reference current? It is one of those, you know, the constant GM, let us say reference current source. Okay. So, that is how you are going to make that reference current. Okay. So, we start again with a reference current, and we do a Wilson current mirror. Let us say you can do a more optimal design instead of Wilson. It is all creativity. You have to be a little creative. Okay. And then we have to work out a PMOS version of this. Once again let us do a Wilson current mirror to create the remaining voltages. Fine. Yes, this is also connected. These are all connected. So, this is my circuit. Okay, I have drawn all the details now. Now, let us put some values. Let us say this is you want to start with I naught by 20. Okay, I naught by 20. Okay. We place this at 2 volts just like earlier, and let us say all the PMOSs require VGST of 0.2 volts, they have VT of 0.4 and therefore, they require a source to gate voltage of 0.6, and let us say all the NMOSs require a gate to source voltage of 0.7. All right. So, I generate 0.7 over here, 1.4 over here. I hope by now you are getting used to this sort of the design. You should be getting used to this design. So, the gate over here is at 0.7. What should be the size? What should be the current here? The current here has to be I naught, remember, whereas the current here has to be I naught by 2. And the remaining I naught by 2 is coming from here. And this is I naught. So, this immediately tells you the relative sizes. If this is I naught by 20, okay, and let us say I keep this relative size as 0.1, this as 0.1, then automatically that means that this should have a relative size of this is 0.1 I naught by 20. What should be the size of this relatively? 2. 2. What about here? This is I naught by 2. So, therefore, the relative size of this should be 1 unit. This should be 1 unit. How about here? 1 unit. 1 unit. How about here? 1 unit. 1 unit. Okay. 2 units. 1 unit each. Okay. In this branch you do not want to waste much current, right. You want everything to be low current, because this is a silent, this is just for DC operating point conditions you have created this branch. So, therefore, these sizes should be similar. So, 0.1, 0.1, 0.1, 0.1. So, that here also the current is I naught by 20. Is this okay? All right. Let us now check out the numbers. Okay. So, the voltage here is 0.7, here it is 1.4. So, the lowest voltage here can be 0.9, 0.5 less than 1.4. Okay, but does this work out? For your PMOS, you need 0.6, 0.6, and as a result you are getting a voltage here, required voltage is 0.8. So, you have a problem, even before you start you have a problem. Okay. So, this Wilson business is not quite working out, this Wilson current mirror is no good. Alright, you need to be a little more aggressive, you can't be using Wilson. Maybe you can skip this device. One possibility is skip this device altogether, you do not really need this device. In which case you do not need to be more than 0.9. Okay. This voltage here is being generated from this, right. So, this device is not needed at all, it is just occupying some area and some headroom. Okay. So, if this is 0.7, then the voltage here is, minimum voltage here is 0.2, which is alright, because here you will get 1.4, here you will get 0.8. Okay, and that is certainly more than 0.2, which is fine. So, the voltage here is 1.4, the voltage here is 0.8, and this device, what is the voltage here? 0.8 minus 0.6, so it is 0.2. So, I am sorry, plus 0.6. So, this is also at 1.4. Now, this is the Wilson action, right. The Wilson action makes sure that the current, reflected current is exactly identical to the reference, right, and that is because both gate and drain are at the same voltage as that of the reference branch. Okay. So, that is why this was 1.4, this is also 1.4, this is also 1.4, fine. Okay. What is the maximum here? Therefore, if this is at 0.8, what is the maximum? This is the output. The output is flexible, right. You will always see that the output is flexible, you will not be able to pinpoint what is the exact voltage there. If you do that, then that is wrong. Okay. The output needs flexibility. What is the voltage here? Maximum. Maximum voltage here is, if this is 1.4, the maximum voltage here is 1.2. Alright, now let us work bottom up. I have got 0.7 here, alright, I have got 1.4 here, and that tells me what is the voltage over here at this source. If this is 1.4, this has got to be 0.7. Okay. I have already decided that voltage 0.7, it is at the drain of the input. So, be a little careful over there, but it is already pre-decided because of the Wilson action. Okay. So, if this is at 0.7, what is the minimum voltage over here? 0.9. Alright. So, you have got a swing from 1.2 volt to 0.9 volt. Now, you had nothing, you earlier also it was 1.2 volt to 0.9 volt. Now, also it is 1.2 volt to 0.9 volt. I had promised you that we will get better, right, and we have not really got any better because of this Wilson action, right. This is no good, this 1.4 volts is no good. Why do you need 1.4 over here, right? This voltage can easily be lower. So, let us not do 1.4 volts, let us make sure that somehow, not this way, some other way. Okay. We are going to make sure that this voltage is not 1.4, we have to be creative. Remember, we did all those optimal current sources and current mirrors and so on. So, this one is no good. right. Let us make sure that we do a little better job over here, and instead of 1.4 I make it, let us say, 1 volt, in which case this is 1 volt, okay. In which case this voltage is set to 0.3, right, and if this is 1, then the lowest voltage at the output is 0.5, and suddenly you have got much more swing available at the output, okay. What about the input? So, I keep this at 0.3, right. What should be the input? The input has to be anything such that, so this, if this voltage is at 0.3, what is VDS? VDS has to be more than VGS minus VT, VSD has to be more than VSG minus VT. In this case, the maximum voltage over here is 1.2, all right. So, the maximum gate voltage at the input, the maximum input common mode voltage is 1.2 minus 0.6. So, the maximum input common mode voltage is 0.6. You can't have more than 0.6 volts, because if you have more than 0.6, this is more than, oh I am sorry, this is not 1.2, this is 1.8. So, the maximum here is 1.8, the maximum here is 0.6 less than 1.8. So, less than anything less than 1.2. We had picked, let us say 1 volt as the input common mode voltage, which is less than 1.2, which is a perfectly good input common mode voltage, because it is halfway between the two power rails. So, let us say the input common mode voltage is 1 volt, in which case what is the maximum allowed voltage here? This is 1 volt. So, the voltage here is 0.4 set, I am sorry, 1 plus 0.6. So, 1.6, okay, which is less than 1.8, and therefore, the maximum voltage here is 1.4, and 0.3 is well below 1.4. So, you are doing a pretty decent job. Okay. Anyway, so this is the folded cascode amplifier. You have to set this side, right. So, we removed this device, we removed this device as well. We need to have a lower voltage over here, right. How do we get a lower voltage? How do you get a lower voltage? You can do other tricks. You can have another current source, small current source, and pull a large amount, have a large device, have a lesser VGS minus VT, all kinds of other tricks you can implement to get a lower voltage out here. It just has to be a stable voltage, that is all that is needed. All right. So, this is the folded cascode amplifier. So, today what we have discussed is swing essentially, right. We have essentially discussed all these voltages, we have discussed headrooms, we have discussed swing, and I have tried to give you a complete picture of what this fully differential amplifier is going to look like. This is fairly complex, right. You have got, we started our course with a 1 transistor setup, and now suddenly you have a setup over here that has 4 plus 4 8 plus 3 11 plus another 4, that is 15 transistors on this picture, right, and another 2 more that I have deleted, right, and then you have to count more inside this and so on, right. So, from 1 we have built up at least 15 if not more. Okay. So, we have come a long way. Alright. So, let us stop over here, and in the next class we are going to proceed further and get more ideas of how the amplifier is going to look like. Thank you.